Welcome to the Deep Dive. Today we're tackling something really fascinating, Jumbo 1.5.
Yeah, this one's definitely caught my eye.
You sent us over the research paper, and our goal for this deep dive is basically to get a clear picture of the key innovations here and what they mean, for AI and for you listening, without getting totally lost in the technical weeds.
Right. We want folks to understand why this matters.
Exactly. We want you to come away with a solid understanding of why this new architecture is a pretty significant step forward, both in, capability and efficiency. Okay, let's unpack this.
Well, what's truly interesting right off the bat is the core problem Jumbo 1.5 is trying to solve. We have these incredibly powerful large language models, but well, when they have to deal with really long pieces of text, they can become kind of slow and frankly need a huge amount of computer memory.
Yeah, the bottlenecks.
Exactly. Jumbo 1.5 directly confronts these limitations.
Precisely. So the paper describes Jumbo 1.5 as a hybrid model. Now, what does that mean for, in practical terms?
Well, it's sort of like this. Imagine a superhero team where each member has a specific power, right?
Okay.
Jumbo 1.5 combines the strengths of two main types of AI components.
Yeah.
The well-established transformer layers, which are great at understanding context within a certain range, and these newer Mamba layers.
Mamba. That's the efficiency piece.
Right. They're really efficient at processing very long sequences of information. And on top of that, it uses a mixture experts, or MOE, system.
Right.
The paper explains that this combination is all about finding, the perfect balance between how much information the model can handle, that's its throughput, how much memory it needs, and ultimately how good its answers actually are.
That balancing act is so important. Think of it like transformer models as being incredibly good at understanding the nuances in maybe a short conversation.
Yeah.
But if you try to have that same level of detailed understanding across an entire book, it just becomes super resource intensive.
Yeah.
Right. Totally.
Mamba, in contrast, can read that entire book much more efficiently. And the MOE layer adds another layer of, smartness by allowing the model to only activate the parts of its brain that are most relevant to the task at hand.
Saving resources.
Exactly, saving even more resources and boosting its overall capacity.
We also learned about two versions of this Jumbo 1.5 thing. A larger one with 94 billion active parameters. Think of parameters as the dials and knobs the model uses to learn.
Yeah, the learning capacity.
And a smaller, more streamlined version called Jumbo 1.5 Mini with 12 billion parameters. What's key, though, is that both of these have been instruction-tuned.
Crucial.
For you, that means they've been specifically trained to be good at having conversations and following instructions, which makes them much more useful for, real-world stuff.
Instruction tuning is really what bridges the gap between a model that just understands text and one that can actively engage with it in a helpful way, like a sophisticated assistant.
Yeah, exactly. But here's where it gets really interesting. Both the large and the mini versions of Jumbo 1.5 can handle an effective context length of 256,000 tokens.
Wow, okay. That's substantial.
The paper highlights that this is the largest among openly available models. Now, why should you care about that massive number? Well, imagine being able to feed, the entire text of War and Peace into an AI and have it actually understand the complex relationships and plot lines throughout.
That's the dream for long-form analysis.
For you, the learner, this means these models can process and understand incredibly large amounts of information at once.
Yeah.
It could potentially revolutionize how you research and learn.
What's fascinating here is exactly how they've managed to combine these different architectural elements to achieve this long context capability. It's not just about, brute force or making one component bigger.
Right.
It's the clever way the Transformer, Mamba, and MOE parts work together that unlocks this ability to handle such vast amounts of text.
And it's not just about how much information they can handle. It's about how efficiently they do it. The paper mentions a roughly tenfold reduction in something called KV cache memory usage.
Yes, the KV cache, always a memory hog.
Right, compared to other models when dealing with that huge 256K token context. Now, even if terms like KV cache sound like tech jargon, what this means for you is pretty significant. Think of the KV cache as the model's short-term working memory as it processes text.
Like RAM for the model's thoughts, kind of?
Sort of, yeah. A 10x reduction means it can remember much more without getting totally overwhelmed or needing massive, expensive hardware.
Which translates to practical benefits.
It translates to more practical applications, lower costs, meaning these powerful tools could become more widely accessible and faster in their responses. Table 1 in the paper really hammers this home, showing how Jamba models use considerably less of this memory compared to models like Mixtral and the different Llama 3 versions.
Yeah, that comparison is stark. And if we connect this to the bigger picture, this focus on efficient memory usage directly impacts who can use these advanced AI models. Lower memory requirements mean that, researchers, developers, maybe even everyday users might be able to run these models on more standard hardware.
Less reliance on the supercomputers.
Exactly, rather than needing access to the absolute most expensive and specialized gear.
Speaking of efficiency, the paper introduces a really clever technique called Experts Int 8 quantization. Now, quantization might sound intimidating,
It often does.
but the basic idea is like shrinking down the digital size of the model's knowledge without losing the important details, making it easier and faster to handle. Essentially, they're taking the weights. Think of these as the core knowledge parameters inside the AI.
The learned information.
Right within the MOE and another type of layer called MLP, and they're compressing them down to an 8-bit integer format, INT8, for storage. But here's the ingenious part. When the model actually needs to use this knowledge for computation, it quickly expands these weights back to a 16-bit floating point format called BF16.
Interesting. So, store small, compute bigger.
Precisely.
The real beauty of this experts-eating technique lies in its practical advantages, though. As the paper points out, the process of compressing and decompressing these weights is incredibly fast, like almost instant when the model starts up.
No long wait times.
Exactly. Unlike some other methods for making models smaller and faster, it doesn't need a long and sometimes tricky calibration process. Plus, it still allows the model to use that more precise BF16 format for the activations.
Which is the data flowing through.
Yeah, the data flowing through the network during calculation. And using BF16 there helps maintain the accuracy of the model's output. It's a smart trade-off.
And get this. This technique can even be used on older, but still powerful, NVIDIA A100 graphics cards.
Oh, that is significant.
Unlike some newer optimization methods like FP8, which need the very latest H100 hardware. Figure 2 in the paper shows this, illustrating that Experts Int 8 either performs as fast as FP8 on the newest hardware or significantly outperforms other compression techniques, especially on those more widely available A100s,
Ow.
and all without sacrificing the quality of the model's answers. So the bottom line for you, the listener, is that this clever technique makes these powerful AI models more accessible and potentially faster, meaning you might see these advanced capabilities integrated into more everyday tools sooner.
Yeah, absolutely. If we connect this to the bigger picture again, this focus on efficient serving, actually running the model through techniques like Experts Int 8, is crucial for democratizing access to advanced AI. It really lowers the barrier for deploying and using these large models in real-world applications, potentially leading to more widespread innovation, which is exciting.
Definitely. Now, the researchers also encountered an interesting challenge during the initial training of Jamba 1.5, something they called activation loss. Apparently, some of these internal signals within the AI network were starting to grow, like extremely large.
The exploding activation problem.
Yeah, which could have caused issues with the accuracy of the model when it was actually being used, right?
This is a really insightful point. While the model was initially trained using a high-precision format called BF16, many systems that run these models in real-world apps use a lower precision format, often FP16, just to speed things up.
For efficiency again.
Right. But if those internal signals, the activations, get too large, they might actually exceed what FP16 can accurately represent. That can lead to instability or just plain errors in the model's responses. It's a known issue.
Okay, so their solution was quite ingenious, it sounds like. They added a small penalty to the training process, specifically designed to discourage these activations from getting excessively large.
Like a gentle nudge during training?
Exactly. They call this the activation loss. And it has an adjustable setting, a factor called alpha. For the larger Jamba 1.5 model, they use a really tiny value for this alpha, 10 to the power of -5.
And the paper emphasizes that this seemingly minor adjustment had a significant impact on keeping those large activations in check, critically, without negatively affecting how well the model learned or how quickly it trained.
That's the cute part.
Yeah. So for you listening, this means the models are just more stable and reliable across different computing environments, even if the underlying technical details are complex. The paper confirms, crucially, that this approach didn't sacrifice the quality of the model's performance.
Good stuff. Okay, let's talk about how well these models actually perform, like the speed and responsiveness.
Right, the user experience metrics.
The paper highlights their excellent throughput and low latency, especially when dealing with those super long contexts we talked about earlier. Figures 3 and 4 in the paper really show this, comparing Jamba 1.5 against other well-known models.
Yeah, throughput, how much info it chews through over time, and latency, the delay before you get an answer.
Exactly. Faster is obviously better on both fronts, especially for you if you're looking to get information quickly.
Those figures are indeed impressive. They show that when processing very long sequences of text, the Jamba 1.5 models maintain a pretty clear advantage in both speed and responsiveness compared to models like the 70 billion parameter version of Llama 3 and Mistral Large 2.
Noticeable difference.
Yeah, and what's particularly striking is that the paper mentions the even larger 405 billion parameter Llama 3 couldn't even be run at the longest context length on the same hardware used for testing Jamba 1.5 large.
Wow. Okay, so Jamba could handle it, Llama couldn't even start.
Right, which really highlights Jamba's efficiency, especially at that extreme scale.
The paper also gives us a peek behind the curtain at how these models were trained. It involved, as you'd expect, a significant amount of computing power.
Loads of GPUs.
Yeah, using NVIDIA H100 GPUs in their own internal training system, employing various fancy techniques to handle the massive size of the models, and just the sheer volume of training data.
The training process itself was quite sophisticated, broken down into 3 key stages. First, they did extensive pre-training on a massive and diverse dataset. Lots of text, code, importantly, multilingual data too.
Building the foundation.
Exactly. Then there was a mid-training phase specifically designed to enhance the model's ability to understand and process long documents, really focusing on that long context skill.
Makes sense.
And finally, they performed post-training to fine-tune the model's specific skills and conversational abilities using carefully curated data and techniques like supervised fine-tuning and synthetic data generation.
Okay, so what does all this sophisticated architecture and multi-stage training actually mean in terms of what these models can do? How do they stack up against other leading AI models in their capabilities?
Well, the evaluation results presented in the paper are quite promising overall. When tested on standard academic benchmarks, things like general knowledge quizzes like MMLU, logical reasoning tasks like GPQA or ARC challenge, and code generation challenges like Human Evil.
Usual suspects.
Right. The Jamba 1.5 models performed at a level that was either comparable to, or in some cases better than, other openly available models of similar sizes. Table 2 in the paper provides a really detailed breakdown of these results across various benchmarks if people want to dig in.
Okay, comparable on the standard test, but what about actual conversation?
Good question. And it wasn't just about passing academic tests. The researchers also evaluated how well these models perform as chatbots in more realistic conversational settings. They used evaluations like ArenaHard and WildBench.
How do those work?
They essentially pit different chatbots against each other and use a powerful judge model, like GPT-4 Turbo in this case, to assess the quality of their responses head-to-head. And Table 3 shows that Jamba 1.5 Large actually outperformed the 70 billion parameter Llama 3.1 in these chatbot evaluations.
Interesting. So better conversationalist, according to GPT-4.
Seems so. But where Jamba 1.5 really stands out, going back to its design goal, is its ability to handle those incredibly long contexts we've been discussing.
The headline feature.
Pretty much. The paper highlights its performance on the Ruler benchmark that's in Table 4, which is specifically designed to test how well models can understand and recall information from very long documents.
Okay.
Jamba 1.5 Mini and Large are the only models listed there with a confirmed effective context length of 256,000 tokens. The researchers even noted they had difficulties replicating some previously reported impressive results for Google's Gemini Pro on this benchmark.
Oh, really?
Yeah, suggesting that the Jamba models currently have a real verifiable advantage in this specific long context area.
That's a big claim.
Mm-hmm.
They also looked at how well the models could understand very lengthy pieces of writing, like entire novels, right?
Mm-hmm.
Using the Infinite Ben Sage dataset.
Correct. That's Table 5. And again, Jamba 1.5 demonstrated superior performance compared to Llama 3 and Mistral Large 2 on these really demanding long-form comprehension tasks.
Consistent strength there.
And finally, while the primary focus of the final training stage was on English, the models also showed surprisingly good performance on a multilingual knowledge benchmark called MMLU. Table 6 shows this, even though only a small fraction of the post-training data was actually in languages other than English.
So the pre-training paid off.
It suggests that the extensive multilingual data used during that initial pre-training phase provided a strong foundation, allowing knowledge to transfer effectively across languages.
It's really encouraging to see this level of performance, especially, in handling those long contexts.
Yeah.
To sort of wrap up our main discussion, it's fantastic that the researchers have decided to release the model weights for both Jamba 1.5 Mini and Lardish to the open source community.
Absolutely huge.
And they've also made their innovative experts-in-date quantization technique publicly available. This kind of open sharing is just so valuable for fostering further progress and exploration in AI.
Yeah, this commitment to open source is a very significant move. By making these advancements freely available, they are really encouraging further research, development, and, the application of this hybrid architecture and their efficient methods for making these powerful models more practical. It accelerates everything.
So to bring it all together for you listening, Jamba 1.5 represents a really exciting advancement in the world of large language models. Its clever hybrid design, combining the strengths of Transformer and Mamba architectures, allows it to achieve a remarkable balance between high performance and efficient resource use, especially when dealing with those incredibly long stretches of text.
That long context efficiency is key.
And that novel experts-in-date quantization technique is a real step forward in making these powerful models more accessible and usable in a wider range of situations.
It truly is amazing how this thoughtful combination of different AI building blocks, along with these smart engineering solutions, unlocks such significant potential. The ability to process such extensive amounts of information efficiently, well, it opens up entirely new possibilities for how AI can be used to understand and interact with the vast amounts of data around us.
The paper also touches briefly on their considerations around ensuring these models are aligned with human values and are safe to use.
Responsible AI, always important.
They mention their commitment to responsible AI development, referencing established guidelines and their collaborations with various organizations. They even highlight having a set of principles that guide how their models are designed to behave.
This focus on responsible development is absolutely critical as these models become more capable and widely adopted. Their proactive approach to these considerations is definitely a positive sign.
Definitely. And with that, we arrive at our final thought for you to ponder. Considering Jamba 1.5's impressive ability to efficiently process these incredibly long sequences of information, what completely new applications might this enable? Think about fields like scientific discovery, historical research, or even just how we manage and understand our own personal knowledge.
When the AI can read the whole library, not just a paragraph.
Exactly. What new questions does this raise about how we might interact with and leverage AI in the future when it can truly grasp and synthesize massive amounts of information with such speed and efficiency?
Yeah.
So, well, it's a lot to consider, and that's exactly where we like to leave you.
Thanks for taking this deep dive with us.